Okay, so these are questions number 6 and also question number 7 of the Magnetic Fields homework booklet. So in question number 6, what we have is we've got a diagram again, and it's showing a rigidly clamped straight horizontal current carrying wire. So basically we've got a wire going along here, it's horizontal and it's clamped so it can't move. And this wire is held midway between the poles of a magnet on a top pan balance. So again, basically a set of weighing scales. The wire is perpendicular to the magnetic field direction. So the field is going in this direction and the current is going this direction, and they're at 90 degrees to each other. We're told that this particular balance, which was zero before the switch was closed, so basically when no current was flowing through here, this was zero, so it read 0 grams, reads 161 grams after the switch is closed. The current is then reversed, so we kind of swap our battery around, so the current's now going the opposite way, and the current is also doubled, so the variable resistor is changed so that the current going through this circuit goes up, and it actually doubles. We want to know what the new reading on the balance would be. So basically what we've got is if we calculate the mass that this balance reads, because again what we find is that the force that acts on the magnets is basically equal to the force that acts on the wire, which is B times I times L, and that's basically an effective weight of the wire. So again, mg is equal to B times I times L. So again, if we rearrange this, we get the mass that this balance reads is equal to this thing. So if we think about this, if we simply change the current around, then this mass would be exactly the same number, but it would mean that the force is in the opposite direction. So instead of the force on the wire being upwards and the force on the magnets being downwards, so this reads 161 grams, actually what would happen is the force on the wire would be downwards, so the force on the magnets would be upwards, and so the balance would read minus 161 grams. So that's what happened if we simply switch the current round in the opposite direction. If we double the current, however, so if this current goes up by 2, then the mass goes up by 2 as well. So therefore the mass, if we double the current, then we'd actually end up with a reading of twice 161 grams. Because we've done both together, we've doubled the current and changed the current, then we'll end up with a reading on this balance of minus 322 grams. And so therefore the answer is A. In question 7, we've got 4 rectangular loops of wire. So this loop A, B, C and D, they're all placed in a uniform magnetic field, and the flux density of this magnetic field is the same for all 4 loops of wire. And the direction of the magnetic field is parallel to the plane of the loops as shown here. So the magnetic field is going from left to right across the page. When a current of 1 amp is passed through the loops, some magnetic forces act on them, and the lengths of the sides of the loops are shown. So we know that this is length L, this has got length 0.5L, that's 0.5L, and so on. We want to know which of these loops experiences the largest couple. Okay, so first of all, the very first thing we know is that if the magnetic field is going this direction, the only parts of these coils that will experience the force are the ones that are perpendicular to our field. So these top parts here won't experience the force at all, and so we can basically ignore those. So when we've got a couple, if we think about this coil here, this side here will experience a force because the current will be, for example, going this way. The current will be going the opposite way down here, so this side will also experience the force of exactly the same magnitude but in the opposite direction. So we have a couple. So if you remember back to your mechanics, a couple is basically equal to the force of one of the sides multiplied by the distance between these sides. And because the force is proportional to the length, so basically we know that the force is equal for a conductor is equal to the magnetic flux density times by the current times by the length of the wire. All 4 of these things, the magnetic flux density is the same, the current is the same, so basically the only thing the force depends upon is the length of the wire. So we can replace F in here basically by L. So really the couple is the L times D. In other words, it's L times the distance between them, this one here. So if we simply work out this distance multiplied by this distance, that'll tell us the size of the couple on this particular coil. So if we do it for this coil, we get 0.2 L squared. If we do it for this coil, we get 0.25 L squared. This one gives us 0.15 L squared, and this one, 0.8 times 0.2, gives us 0.16 L squared. So therefore the one with the largest couple is B. So that was questions number 6 and 7 from the magnetic fields homework booklet.